Well, it's the first time I've spoken in an energy or automotive show, because normally when I give talks it's about looking through people's clothing, but you have to look me up on LinkedIn to find out why. Anyway, in 2009 I got bored with looking through people's clothing and thought I'd use some of my lessons I've learned in applied physics to start looking at energy and how I could take my house here in Cornwall off the grid. We started a company with my business partner Mike Bennett, with friends. He'd actually done a few builds on £1 million properties that used all variety of renewable energies and found that actually, he couldn't quite work out how they were saving any money or saving any carbon. So he got me to look at a few of them, and we decided that actually they were pretty poor in what they set out to achieve. So we looked at all the standards of photovoltaic applying to my house, and actually I'm at the bottom of a valley, so I lose about an hour of daylight at the end of each day. I should say actually, the conditions we set ourselves was take my house off grid, no subsidy, pay back in 4 to 5 years. And I think that's key for any business that's really going to grow. It's got to be profitable and it's got to make savings for the person who puts the investment into the equipment. So under those conditions, 4 to 5 year payback, we looked at the solar photovoltaic, and even then in 2009 you were looking at 12 to 20 years with subsidy. I live at the bottom of a valley, again, not much wind, unfortunately for me. Solar hot water is all right in the summer, but actually my roof on my property is slate rag, which wouldn't take the weight of the things that we wanted to put on there, so it wasn't suitable. And then ground source heat pump looked pretty useful, but actually to dig my garden up was going to cost about £12,000 to put the system in. The actual pumps and that were quite reasonable. And then I had this eureka moment. I sort of found this book, Chinese Biogas Manual. I recommend you buy it. In fact, there's 3 of them. In the 70s, the Chinese had 30 million locally based anaerobic digesters. And they were primarily, at the time, this is before we even knew that methane was a potentially global warming gas. I should say my background is in climate, supplying technology to climate scientists. So I was familiar with the sort of problems, but at the time it was more about the ozone hole than climate change in the 1970s. And this was all about actually deforestation, tackling the problems of deforestation, people cooking on twigs and things that they were pulling. And so the Chinese had this whole program which shows you how to build anaerobic digesters and how to operate them. It's a fantastic program. Unfortunately, there was something similar going on in India around about the same time, but unfortunately it fell apart because the people who were trained to use the digesters eventually died and moved on, and the skills was lost. But you can take a little graphic like this out of it, and it gives you an idea of what you can do. And some of these numbers, actually, I should say, are a little bit dubious. I think they're a little bit optimistic, but nevertheless, they're not that far out. And so if you get 1 cubic metre of biogas, it's equivalent to about 0.7 kilograms of petrol. It's actually more like 0.5. And you can run a 1 horsepower motor for 2 hours. You can drive a 3-ton truck, 2.8 kilometres, and 1.25 kilowatts of electricity. And of course, you get the heat as well because it's produced locally. If you can look at the bottom right, in between the text, you can see 3 red dots. This is basically a graph of energy versus mass along the bottom, energy versus volume along the side. If you want to make a rocket, you want something that's got lots of energy and it's light. And so you choose hydrogen, liquid hydrogen, in fact. If you want to drive a vehicle in the green circle, then you need to have something which is part way. I should say right at the top, you've got anthracite, which is incredibly energy dense. And you need anthracite if you're going to have a power station, because you've got to move a lot of energy around. Okay, so it shows you the different applications: power stations, rockets, heavy vehicles. Okay, and if you want to drive a heavy vehicle, then the only sort of gas that really works in its liquid form is methane. And I should say liquid natural gas and methane are not the same things by any chalk. As you get further and further into the industry, you find that out. So we came up with this idea that you take the biomass, whatever form it is, as long as we can digest it anaerobically, and we don't get involved in anaerobic digestion, I should say, really, we don't want to anyway, and then you turn that into biogas, and then if you liquefy it, you've got a fuel which is actually pretty similar energy density to petrol, propane, butane. You've got your methane, if you can store it, you can then transport it and you can use it to create CNG and LNG. And you can either power vehicles or you can use it as a direct replacement for heat and electricity. I should say the first engines were gas engines in the sort of late 19th century. What's left after you've done all of that from the digester is a very rich digestate, which you put back on the land, and that's all the nutrients that that plant took up during its lifetime. So provided you put the same digestate back on the same land, and I must stress that actually, if you start putting digestate on the land from other land, you're putting nutrients from that land in the wrong place. So provided you close the cycle, then you have got a cycle which is completely sustainable and zero carbon. So it seems like the perfect solution when you start going through this. And there's a lot of caveats, and people who've worked in the anaerobic digestion world on the large scale will know that there's lots of challenges in meeting that. But it seems like, biomass to methane is the perfect solution. It has a zero carbon footprint, effectively. I will come back to that in a second. It's a better fuel for combustion in engines than diesel or petrol. A pure methane engine has the highest WOB number you can have, so you can run at very high compression ratios to get very high efficiencies. And the only thing that should come out the tailpipe is CO2 and water, so it completes the cycle. Because of its energy density, it's really the only viable fuel that can replace diesel, for the reasons that Penny just said. As a liquid, it's very transportable. You can move it, so you can use it where it wasn't necessarily generated. And as a fertilizer, it adds back to the economy. Now, I'll talk a little bit about that on the farm, but actually, basically, by putting the digestate back, you're putting a lot of carbon back into the soil. And that is a huge amount of carbon that goes back in, because the parts you can't digest are mostly carbon in the form of lignin. It's incredibly safe to handle methane when you compare hydrogen to it. It's one of the safer gases. And again, so it sounds like the perfect solution. And then we started to develop a business model around local generation of biomethane using the waste products. And we hit this problem, it's a financial problem primarily, is that most of our biomass is produced in the spring, summer and autumn, but our peak energy is in the winter. So what's the problem? Store it like propane, butane, problem goes away. I should say that that's reversed in places like Canada and California, where already it's reversed because they're using more energy on air conditioning than they are on heating. So if you're in California, for example, that would be the opposite. Summer would be where you'd use most of your energy. Liquid methane, in my ignorance, I thought simple, and then I started to look at some of the physical properties of methane. And it turns out you can only store it as a cryogen. It's like nitrogen, argon, and oxygen. And for those of you who are not aware of how cryogenic liquids are stored, if you imagine a pressure cooker in reverse, a pressure cooker, everyone knows, you put a flame under it, you heat it, get it boiling, and eventually you release the pressure with a valve, you get a higher temperature in your water, which cooks faster. Well, that's the same for cryogenics, except now that heat going in is just from the surroundings, so you want to stop that. Otherwise, eventually, if you don't, the pressure isn't released, then it will explode. And that's not it might explode, it will explode. Of course, it's not a problem for nitrogen. All of the standard cryogenic technology is based around early technologies coming out of the Second World War, which used cryogens a lot. They were used in the space program. Didn't really care about emissions in those days. And a lot of that technology comes from just storing nitrogen. Nitrogen you can release very easily because it's part of the atmosphere. Liquid oxygen you can release because it's part of the atmosphere, as is argon. But methane explodes. This is exactly how the technology on a liquid natural gas truck works. It operates at a pressure of around about 8 to 13 bar. And that high pressure requires a circular construction on the tank. So that limits the amount of energy, or it limits the amount of volume, and in turn the energy that you can store within a given length. So the challenge is always to get as much energy onto the vehicle as possible. But if you leave that truck unattended for around 5 days, eventually that methane will be vented. Now, they get around that in the industry because those trucks are losing money if they're standing still. So whilst you're drawing the gas off, that pressure never gets to a point where it vents, so you can manage it. But if a truck breaks down, it is a problem. You've got to think about where that gas goes. You've got no condition over the LNG, and I say liquid natural gas fuel qualities. Natural gas is made of a variety of gases. It could be CO2, butane, ethane, propane, xylene, a few other nasty little things in there as well. But if you don't do anything with it, you lose 1 to 2% a day if it's unattended. That doesn't sound a lot, but methane is 25 to 35 times worse than carbon dioxide as a global warming gas. Now that depends on where you read, the literature you use. It's quite a difficult thing to calculate. So if you leave it unattended, 1% loss on a 200 kilo tank equates to 2 kilos of lost methane. Multiply that by 35, That's 70 kilos of petrol equivalent energy for standing still. Okay? So how do you manage the emissions? Venting is not an option because of that big number at the top there, 25 to 35. And also methane slip through the tailpipe. Not all engines burn all the fuel. Some of that ends up out the tailpipe. So if you've got 1% methane slip, similar problems, you have to multiply all those numbers. So these are the Achilles heels of methane: storage and emissions. Okay? And if you can solve those two problems, you've now got a perfect fuel. And this is what we came up with in 2011. It's ridiculously simple, really, but actually it's now a patent in the US. If you take a standard liquid nitrogen tank, fill it full of liquid methane, eventually that gas will vent. But instead of venting to atmosphere, an inert gas, it's an active gas. It's got all the energy contained within it. And methane actually contains 6 times the amount of energy it's needed to liquefy itself. If I was to compare that with hydrogen, it would need 3.5 times the amount of energy it contains. Okay, so it's 1/6 versus 3.5. And that's because hydrogen is a liquid at 20 degrees Kelvin. Methane's a liquid at 112. So how does it work? We take the gas that would otherwise be vented, we run it through an engine, fuel cell, generate some power, use that power to charge a battery, and when the tank is about to vent, we switch on a cryocooler inside the tank, we bring the temperature down, recondense the gas, and that venting stops. Okay, now with a combination of some really novel cryogenic design taken from the space industry, where they're always trying to keep as much gas in the tank, and combination of this, we can increase the hold time by about a factor of 10. I won't go into the patent, but you can see it's real. This is going through in Europe, I should say, as well at the same time. So basically, we use that gas that would be vented to extend the hold time of the tank. So now we have a fuel that is non-venting. It's a liquid fuel that has similar energy to diesel. There's no need to connect this to the grid. We don't need any power, so it's standalone. And if we use the Internet of Things, we can control it. So we can switch it on and off and monitor it. It means it can be unattended. And we can use those free biogas feedstocks wherever they are, be it food or plant material, to create that energy anywhere in the world. We don't need a grid network. Okay? We don't need a gas mains. This is completely a game changer. The interesting thing is that fuel as a liquid is worth around about 4 to 6 times more than the electricity it could produce if you were without subsidy. So you've now got something which is commercially viable. You can transport it to wherever you need to use it from the place where it's being created. But also because you can store it, you sell it when you get the best price, so that price is now driven by the open market. We can use it as fuel for backup generators on solar parks. We have a big problem in Cornwall where we're based. There's huge numbers, anyone who's visited there's huge numbers of solar parks. But of course they're only really taking that full grid capacity. They might have a huge capacity, but they're only using it for a few hours of the day. What do you do when it's dark on a cold night in November? Well, if you can use a biomethane powered backup generator, you can use that grid access to power the grid. It's a fuel for HGVs and tractors, and we're talking to and working with some of the biggest players in the game. And it's a direct replacement for town gas for heat and cooking. I should say that propane at the moment is around £2.50 a kilo. Biomethane for a truck is around 80p. So if we can sell it to people who just do their cooking with it, it's 3 times more valuable. We believe that it's a paradigm shift in the energy market. It enables storage of energy on a global scale because biomass exists on a global scale. And it's the first intermittent or non-intermittent fuel to span the seasonal variations. We can switch it on and off instantly. So whilst it may not be the most powerful generator on that park, we only switch it on when we need it. And when there's no wind and when there's no sun, we definitely need something to replace them. And it's completely sustainable. Provided you put that digestate back where it came from, then you close the cycle. So there's no end to it. The financial incentive is profit. Okay, so, I'm not really a capitalist, but actually in this instance, I think profit is a good thing because it's the only way that this energy is going to be taken up. So the incentive is there from a financial point of view, and the fact it's good for the planet is an added bonus. So how do you take this to reality? This is a dairy farm in Cornwall. Now, I should say the we treated this like a gas well. We only came across it by accident. It's a unique farm, probably. Jim Foote and the family there literally built this off their own back with no subsidies, no grants, because they wanted to deal with their slurry and they realised there was a lot of energy in it. So basically it's a slurry lagoon that's sealed and takes the slurry from around about 200 cattle. It produces around about 50 to 100 cubic metres per hour of gas, depending on the season. To put that in context, that's half a tonne of liquid methane a day to 1 tonne of liquid methane a day. They haven't got great connection to the grid, so they can't export the electricity. They've got no gas connections, so they can't inject. There are 300 digesters in the country that are injecting electricity and gas. There are 120,000 farms in the country. Okay? There are 2,500 dairy farms of this sort. There are 600 dairy farms in Cornwall alone. So whilst they might not be producing huge amounts of gas, a typical industrial digester might be putting out 1,000 to 2,000 cubic metres per hour. These are only putting out 50 to 100, but there's hundreds times more of them. The interesting thing was, even if they burnt all that gas to create electricity, they couldn't do anything with it because they only had a 30 kilowatt connection to the grid. They'd have to pay to get a substation put on. And the other problem with it is that if you don't do anything with it, that gasometer, the bag on top, fills up in 24 hours. It produces 6 times more gas than the farm can utilise or export. So looking at a conventional dairy farm, this is the situation you've got. You've got basically an uncovered slurry lagoon. Rainwater goes into that lagoon, dilutes it. The farmer has to spread it, otherwise it overfills. Now he's spreading it when there's rain. The slurry runs off the ground, runs into the river, pollutes the river courses. And so we can, this kind of setup is typical in a nitrogen vulnerable zone. The farmer can't access AD, even though he might want to, because he hasn't got any access to the grid, so he can't generate any money, so therefore he can't raise the capital. If we take the top system, this is how we found Chynareth. Basically, the slurry goes into a covered lagoon. The rainwater is taken off. Jim was taking the biogas, putting it through a CHP. He was to get around about £30,000 a year with subsidy for the electricity he was producing. But the great thing was, because that rainwater wasn't going into the slurry, he only had to spread his slurry when he wanted to, and that was generally when the ground would absorb it, which meant there was no runoff into the zone. So he's got the environmental agency approval to use and spread at other times of the year that other farmers can't. So what Benamann came up with was a way of actually taking that gas and cleaning it and separating it and then converting it to liquid. We still need a CHP to do that at the moment, so we have to take some of that gas to generate the power to process the other. But what it means is that Jim now gets a second revenue stream, which is completely unrelated to dairy. He can now sell that, or we sell that gas on his behalf, and we're looking at a variety of customers. It's quite exciting, the number of people who want to use it. And he can sell it into transport, he can sell it into heat and gas, or we sell it into heating. And also there is a benefit of CO2, which we're actually not using or even including in our business model at the moment. You can see here, if you look at the green circles, in his initial instance, it's actually a very simple, cheap system on the farm. And the reason Jim went down the road that he did was because he didn't want to pay all the money for the traditional combined heat and power systems. But he was looking at around about a return of investment around about 13.5 years. And when you put on the Benamann cycle, that comes down to around about 8.7. I should say there are other impacts as well for this. So we're not quite there yet in a return in 4 to 6 years, but we're getting close. But in terms of what it does for developing applications, if you think about anywhere in the third world where they've got huge amounts of biomass, but they've got all the sorts of problems where they're using fires to get off pollution, the animal waste and firewood are burnt for cooking and lighting. It's labour intensive, the farming. A lot of the food, something like 50% of the food is lost in these places before it even gets to the market. And you've also got a lot of parasites and pathogens in the animal dung, which ending up in the food chain. And they have to import fertilisers because they don't have a way of any other way of boosting their crop yield. Now, if you include the biomethane aspect of this, effectively they get light, so they can start to be educated. You can take their digestate and put it on the ground and remove the need for fertilisers. In India and Africa, compressed natural gas, or in this case it would be compressed biomethane, is already being used in vehicles. All the tuk-tuks in India, for example, are using them. You can use the waste CO2 out of our products, I should say, as cold CO2. So you've got refrigeration without any mechanical requirement. using the dry ice. You've now got fuel which you can power vehicles, so you take the labour-intensive part out of the farming. So this is sort of where we're heading for. It's like a very local, create the energy, use the energy where it's created. If you then include the Internet of Things in this, you've now got something which can be expanded globally. So we won an award from the European Space Agency to do a one-year feasibility contract to look at the exploitation of this using SATCOMs, because the one thing we have to do at the moment is we still have to connect to the internet if we want to control it. But of course you don't need to do that if you've got a satellite receiver on top of all your equipment. And so we're developing a business model around the local generation and use of biomethane, all enabled by the ability to store. I should say none of these models stack up if you can't store it. Immediately, as soon as you start to want to create enough methane to make money, the storage becomes an issue. You have to turn it into liquid, reduce its volume down to 1/600th and make it transportable. So taking this on board, what do we think the future holds? Well, I think it's going to be an intelligent network of localized liquid biomethane storage systems and supplying energy on demand. I think intelligent networks of nano. These, believe it or not, Jim's digester is termed micro. It's about 50 meters long by 25 meters wide by about 17 meters deep. But how anything that big can be micro, I don't know. But actually, from the amount of gas it puts out, it's actually deemed to be a micro digester. But we're looking at much smaller digesters than that. We're looking at the sort of digesters that you might use in a small village. I think efficient zero-slip methane engines or methane to power systems are going to be a requirement. 1% methane slip is a killer for this. Okay, now they're already starting to meet that using catalytic converters on the pure methane engines. But I think there is a lot of work that can be done that can actually reduce a specifically designed methane engine, which can be much more efficient and have zero methane slip. So that's where we see the technology. Thank you.